Okay, hi. So we're doing Module 5 of Switching, Routing and Wireless Essentials, which of course is Spanning Tree Protocol Concepts. So we're going to look at how STP enables redundancy in a Layer 2 network. And so we'll look at some common problems in a redundant Layer 2 switch networks. We'll look at how Spanning Tree Protocol operates, and we'll look at the evolution of STP. So there's been newer versions since, and some modifications by different vendors. All right, so the purpose of STP. So this topic covers the causes of loops in Layer 2 networks and briefly explains how Spanning Tree Protocol works. Redundancy is an important part of the hierarchical design for eliminating single points of failure and preventing disruption of network services to users. Redundant networks require the addition of physical paths, but logical redundancy must also be part of the design. Having alternate physical paths for data to traverse the network makes it possible for users to access network resources despite path disruption. However, redundant paths in a switched Ethernet network can cause both physical and logical layer 2 loops. Ethernet LANs require a loop-free topology with a single path between any two devices. A loop in an Ethernet LAN can cause a continued propagation of Ethernet frames until a link is disrupted and breaks the loop. Okay, so Spanning Tree Protocol is a loop prevention network protocol that allows for redundancy while creating a loop-free Layer 2 protocol. STP logically blocks physical loops in a Layer 2 network, preventing frames from circulating the network forever. So the whole thing about it circulating forever, there's a TTL field in Layer 3, but there is no such animal in Layer 2, and so the packets will just keep going and going. And so especially when you have broadcasts in the thing, it really makes it worse. And so basically here we've got redundancy. If one of these links were to break, you would still have connectivity. But of course, with all of the links active at the same time, you've got a loop. And so Spanning Tree would disable one of those links to eradicate that loop. Okay, so it compensates for a failure in the network by recalculating and opening up previously blocked ports. And so from the previous slide, of course, this one was disabled. Now this link is dead, and so it will re-enable this link so the traffic will still get through. Okay. So the issue is redundant switch links. Path redundancy provides multiple network services by eliminating the possibility of a single point of failure. When multiple paths exist between two devices on an Ethernet network and there is no spanning tree implementation on the switches, a Layer 2 loop occurs. A Layer 2 loop can result in MAC address table instability, link saturation, and high CPU utilization on switches and end devices, resulting in the network becoming unusable. Layer 2 Ethernet does not include a mechanism to recognize and eliminate endlessly looping frames. Both IPv4 and IPv6 include a mechanism that limits the number of times a Layer 3 networking device can retransmit a packet. A router will decrement the TTL in every IPv4 packet or hot limit field in every IPv6 packet. When these fields are decremented to 0, a router will drop the packet. Ethernet switches have no comparable mechanism for limiting the number of times a switch retransmits a Layer 2 frame. STP was developed specifically as a loop prevention mechanism for Layer 2 Ethernet. Okay, without STP enabled, Layer 2 loops can form, causing broadcast, multicast, and unknown unicast frames to loop endlessly. This can bring down a network quickly. When a loop occurs, the MAC address table on a switch will constantly change with the updates from the broadcast frames, which results in MAC database instability. This can cause high CPU utilization, which makes the switch unable to forward frames. An unknown unicast frame is when the switch does not have the destination MAC address in its MAC address table, must forward the frame out all ports except the ingress port. So that's the flooding, basically. A broadcast storm is an abnormally high number of broadcasts overwhelming the network during a specific amount of time. Broadcast storms can disable a network within seconds by overwhelming switches and end devices. Broadcast storms can be created by hardware problems such as a faulty NIC or from a Layer 2 loop in the network. Layer 2 broadcasts in a network such as ARP requests are very common. Layer 2 multicasts are typically forwarded the same way as broadcasts by the switch. IPv6 packets are never forwarded as Layer 2 broadcast. ICMP version 6 neighbor discovery uses Layer 2 multicasts. So the end result's much the same. A host caught in a Layer 2 loop is not accessible to other hosts in the network. Additionally, due to the constant changes in its MAC address table, the switch does not know out of which port to forward unicast frames. To prevent these issues from occurring in a redundant network, some type of spanning tree must be enabled on the switches. Spanning tree is enabled by default on Cisco switches to prevent layer 2 loops from occurring. Okay, so spanning tree algorithm was invented by Radia Perlman while working for Digital Equipment Corporation and published in 1985 paper, Her Algorithm for Distributed Computation of a Spanning Tree in an Extended LAN. Her spanning tree algorithm creates a loop-free topology by selecting a single root bridge where all other switches determine a single least cost path. STP prevents loops from occurring by configuring a loop-free path through the network using strategically placed blocking state ports. The switches running STP are able to compensate for failures by dynamically unblocking the previously blocked ports and permitting traffic to traverse the alternate paths. Okay, so how does spanning tree algorithm create a loop-free topology? As we said earlier, the first part of the process is selecting a root bridge. So the bridge or switch is a reference point for the entire network to build a spanning tree around. Then we block redundant paths. So STP ensures that there is only one logical path between all destinations on a network by intentionally blocking redundant paths that could cause a loop. When a port is blocked, user data is prevented from entering or leaving that port. And so you then create a loop-free topology. A block port has the effect of making that link a non-forwarding link between the two switches. This creates a topology where each switch has only a single path to the root bridge, similar to branches on a tree that connect to the root of a tree. Now, of course, they need to recalculate in the case of a link failure. So the physical paths still exist to provide redundancy, but these paths are disabled to prevent the loops from occurring. If the path is ever needed to compensate for a network cable or switch failure, STP recalculates the paths and unblocks the necessary ports to allow a redundant path to become active. STP recalculations can also occur anytime a new switch or inter-switch link is added to the network. Okay, operations. So as we said, it builds a loop-free topology in 4-step process. First, it elects the root bridge. Then it elects root port. So that's on all non-root bridges. They choose which port is the quickest port to the root bridge, and so that is the root port. Then you elect designated ports, and then you have alternate ports. So during STA and STP functions, switches use bridge protocol data units to share information about themselves and their connections. Bpdus are used to elect the root bridge, root ports, designated ports, and alternate ports. Now each Bpdu contains a bridge ID that identifies which switch sent the Bpdu. The BID is involved in making many of the STA decisions, including root bridge and port roles. The BID contains a priority value, the MAC address of the switch, and the extended system ID. The lowest BID is determined by the combination of these three fields. Now, bridge priority is basically a number that's put in front of the MAC address, and basically, well, previously it was always just how many bits? Not 16. A 16-bit number, and that was it. But now extended system ID has sort of changed that, where basically it's still a 16-bit number, but it actually only uses some of those for priority, and the rest are actually have the VLAN ID in it, because we'll talk about per VLAN spanning tree later, and that's the reason why they've done it that way. And so the first part is the bridge, the most significant number, so the leftmost bits of bridge priority. Then you've got extended system ID, and then you've got the MAC address. Now, the default value for a bridge ID, a bridge priority, is 32,768, which is of course halfway through the range. And so if all bridges have that same default value, it is then the MAC address that is the determining factor of who will be the root bridge. And so, of course, because the root bridge is how all traffic paths are calculated, you don't just leave it to chance. You should actually manipulate the bridge ID so that you have a preferred switch, typically a core switch, that will end up being your root bridge. And so it's through that bridge ID, bridge priority, that you can actually manipulate the election process. So the STA designates a single switch as the root bridge and uses it as a reference point for all path calculations. Switches exchange BPDUs to build a loop-free topology, beginning with selecting the root bridge. And so, as you can see here, they all have their MAC address, and then the priority number is before it. And yeah, so these two are default priority values. This one has had it manipulated to make it lower, and so this will end up being the root bridge. If it had been the default priority value, you'd notice that I'm assuming this is the lower number, so this would have ended up being the root bridge by default. But because someone's manipulated the priority, that's where it's gone. Okay. All switches in the broadcast domain participate in the election process. After a switch boots, it sends out a Bpdu frames every 2 seconds. These Bpdu frames contain the bridge ID of the sending switch and the bridge ID of the root bridge, known as the root ID. The switch with the lowest BID will become the root bridge. At first, all switches declare themselves as the root bridge with their own BID set as the root ID. Eventually, of course, they will learn the bridge IDs of other switches, and in all instances except for one, they will learn that they are not the root bridge. And so they will all agree on who is the root bridge. Okay. Now, because the default bridge ID or bridge priority is 32.768, it is possible for 2 or more switches to have the same priority in the scenario. Where the priorities are the same, the switch with the lowest MAC address will become the root bridge. The administrator should configure the desired root bridge with a lower priority number. In the figure, all switches are configured with the same priority. Here the MAC addresses become the deciding factor as to which switch becomes the root bridge. The switch with the lowest hexadecimal MAC address value is the preferred root bridge. In this example, S2, and they haven't actually lowered the priority there anyway, but as I said, that's the one that would have become the root bridge. In this example, S2 has the lowest value for its MAC address and is elected as the root bridge. Note, the priority of all switches is 32.769. The value based on the bridge priority of 32.768, and of course you've got a default VLAN number of 1, and so that's why it ends up being 32.769. Now, basically, once the root bridge has been elected, the spanning tree then starts determining the best paths to the root bridge from all other bridges. So the path information, known as the internal root path cost, is determined by the sum of all the individual port costs along the path from the switch to the root bridge. When a switch receives a BPDU, it adds the ingress port cost of the segment to determine its internal root path cost. The default port costs are defined by the speed at which the port operates. The table shows the default port costs suggested by the IEEE. Cisco switches by default use the values as defined in the IEEE 802.1d standard, also known as the short path cost for both STP and Rapid Spanning Tree Protocol. Although switch ports have a default port cost associated with them, the port cost is configurable. The ability to configure individual port costs gives the administrator the flexibility to manually control the spanning tree paths to the root bridge. Okay, so we have 802.1d, we have a port cost of 2 for 10 gig, we have a port cost of 4 for 1 gig, we have a port cost of 19 for 100 megabit, and we have a port cost of 100 for 10 megabits. And so with 802.1w, which is Rapid Rstp, of course they've upped the values just to make it a little more consistent with the actual speeds. So it's 1,000 times faster here, but of course that's what That's what happens here, isn't it? So, oh, well, it's 10 times. Sorry, 10 times bigger for each one. And so, yeah, so yeah, that's what they've done there. They've made it a little more consistent because, sorry, the previous one, well, I think at the very most there was 100 megabits at the time. So these are sort of bodged in to just make them less than that, while this is a more consistent structure. Okay, so root ports. After the root bridge has been determined, the spanning tree algorithm is used to select the root port. Every non-root switch will select one root port. So the root bridge doesn't have any root ports because it is the root bridge. It doesn't need to use a port to get to the root bridge. While the others do have a root port, and of course that is the lowest cost link to the root bridge. And so, as I said, the root bridge is the port closest to the root bridge in terms of overall cost of the root bridge. This overall cost is known as the internal root path cost. The internal root path cost is equal to the sum of all the ports along the path to the root. The root bridge is shown in the figure. Paths within the lowest cost become preferred, and all other redundant paths are blocked. In the example, the internal root path cost from S2 to the root bridge S1 over the path 1 is 19, while the internal root path cost over path 2 is 38, because path 1 has the lowest overall path cost of the root bridge. It is the preferred path, and fast Ethernet 0/1 becomes the root port. So we'll talk about switch 2, so it's this one here. So of course it's fast Ethernet, so it's 19 per link. This has only got one link, and so it's 19, while this one of course goes over 2, so it's going to end up being 38. Okay, so designated ports. Every segment between two switches will have one designated port. The designated port is a port on the segment that has an internal root path cost to the root bridge. In other words, the designated port has the best path to receive traffic leading to the root bridge. What is not a root port on a designated port becomes an alternate or blocked port. All ports on the root bridge are designated ports because, as we said, they're not root ports. If one end of a segment is a root port, the other end is a designated port. So it's normally the way you look at it. If you've got a root port, the other end will be a designated port. All ports attached to end devices are designated ports. On segments between two switches where neither of the switches is a root bridge, the port on the switch with the least cost to the root bridge is a designated port. Okay, so alternate or blocked ports. Blocked ports is the original STP name. Alternate port is what Rstp calls it. If a port is not a root port or a designated port, then it becomes an alternate or backup port. Alternate ports are in discarding or blocking state to prevent loops. In the figure, the spanning tree algorithm is configured that fast Ethernet 0/2 on switch 3 is in a blocking state and will not forward Ethernet frames. All other interswitch ports are in a forwarding state. This is a loop prevention part of STP. To elect a root port from multiple equal cost paths, when a switch has multiple equal cost paths to the root bridge, the switch will determine a port using the following criteria: the lowest sender bridge ID, the lowest sender port priority, and the lowest sender port ID. So with the lowest sender bridge ID, this topology has 4 switches, with switch 1 as the root bridge, this one over here. Port fast Ethernet 0/1 on switch 3, and port F0/3 on switch 4 have been selected as root ports because they have the root path cost to the root bridge for their respective switches. S2 has 2 ports, fast Ethernet 01 and 02, with equal cost paths to the root bridge. The bridge IDs of S3 and S4 will be used to break the tie. This is known as the sender's bridge ID. S3 has a bridge ID of X S4 has a bridge ID of Y. Because S4 has the lower bridge ID, that is the one that will be used. And so that will be the root port. That one will be an alternate port. Okay. The lowest sender port priority. This topology has two switches which are connected to equal cost paths between them. S1 is the root bridge, so both of its ports are designated ports. S4 has two ports with equal cost. Because both ports are connected to the same switch, so the sender's bridge ID is the same thing. So that's a tie. Next is the sender's port priority. And so the default port priority is 128, so both ports have S1 on S1 have the same port priority, so that is also a tie. However, if either port was configured with a lower port priority, S4 would put its adjacent port in forwarding state. The other port on S4 would be in the blocking state. And so basically, yeah, that would decide which port. And so, but of course that was a tie. And so the lowest sender port ID. So the last tiebreaker is the lowest sender's port ID. Switch 4 has received Bpdus from fast Ethernet 0/1 and 0/2. The decision is based on the port ID, not the receiver's port ID, because the port ID of F0/1 and S1 is lower than F0/2. The port F6 on switch 4 will be the root port. And so that is the one will be connected to S1. And so F05 will become put in the blocking state as an alternate port. Okay, so timers and port states. So Stp Convergence requires 3 timers as follows. So there's hello timer. The hello time is the interval between Bpdus. Normally that's 2 seconds, but you can modify it anywhere between 1 and 10 seconds. Okay, now, then there is the forward delay timer, and that is the time that is spent in the listening and learning states. And so basically there's 15 seconds is the default time. And so you've got that for both listening and learning. And then you've got your max age timer, and that is the interval that the switch waits before attempting to change the STP topology. And so basically, as we've said up the top, there's a hello timer. Every 2 seconds, bridges will normally send out a Bpdu. After 20 seconds, the max age timer is when you go, oh, okay, well, that bridge is no longer up for whatever reason. I can't communicate with it. So they wait 20 seconds, and so that's your max age timer. And so from there, you then go through the forwarding delay twice, once for listening and one for learning. And that's why you often get a 50-second delay with spanning tree protocol. And so basically, you wait 20 seconds. Oh, that bridge is dead. And then you wait 15 in listening and another 15 in learning. And so that's 50 seconds. So that's often why you see the amber light on switch ports when they start up. Now, default times can be changed on the root bridge, which dictates the value of these timers for the spanning tree domain. Okay, so the timers and port states. STP facilitates a logical loop-free path throughout the broadcast domain. The spanning tree is determined through information learned by exchanging Bpdu frames. If a switch port transitions directly from blocking state to forwarding state without information about the full topology during the transition, the port can temporarily create a data loop. For this reason, STP has 5 port states, 4 of which are operational states, as shown in the figure. The disabled state is considered non-operational. Okay, so we have blocking is where we start out, and so there's no Bpdus received, and of course we have your max age of 20 seconds. Then we transition to listening for 15 seconds, and And then after that, we transition into learning, another 15 seconds, and then forwarding. And now, of course, from if the link comes up, again, you're in blocking until STP determines if the port is root or designated. But anyway. All right. So what can we do with these different states? Now, tables, basically, blocking means if you receive Bpdus, cool, we'll deal with them. But we won't update the address table, and we won't forward data frames. In listening, we will send and receive Bpdus, but nothing else. We don't update the MAC address table, and we don't do any forwarding data frames. In learning, again, we send and receive Bpdus, but we also update the MAC address table. That's what we're learning, actually, is where some MAC addresses are, just so we don't have to flood everything once we're up. But we don't actually forward any data frames. We see them, we take notice of where they came from, but we don't forward them. Then, of course, we transition to forwarding, and then, of course, we still send and receive Bpdus. We still update the MAC address table, but we also forward data frames. Now, in disabled state, so if you don't under shutdown, nothing happens, of course. So STP can be configured to operate in an environment with multiple VLANs. And in per VLAN spanning tree, PVST, there is a root bridge elected for each spanning tree instance. This makes it possible to have different root bridges for different sets of VLANs. STP operates in separate instances of STP in each individual VLAN. If all ports on all switches are members of VLAN 1, there is only one spanning tree instance. But you can actually sort of manage traffic a little better if you have multiple spanning tree instances running, the different VLANs, and so that's why they do it. Okay, so the evolution of STP. So many professionals generically use spanning tree protocol to refer to various implementations of spanning tree, such as rapid spanning tree, multiple spanning tree. In order to communicate spanning tree concepts correctly, it is important to refer to the implementation or standard of spanning tree in that context. So the latest IEEE documentation on spanning tree says that 802.1d has now been superseded by rapid spanning tree, or STP, which is so the IEEE uses STP to refer to the original implementation of spanning tree, and Rstp to describe the version of spanning tree specified in 802.1d 2004. Because the two protocols share much of the same terminology and methods for the loop-free path, the primary focus will be on the current standard and Cisco proprietary implementations of STP and Rstp. Cisco switches running iOS 15 or later run PBST Plus by default. This version incorporates many of the specifications of 802.1d 2004, such as alternate paths in place of former non-designated ports. Switches must be explicitly configured for rapid spanning tree mode in order to run rapid spanning tree protocol. Okay. So STP, of course, came out, and basically it refers to the version from 1998 or earlier. It's also called common spanning tree. It assumes one spanning tree instance for the entire bridge network, regardless of the number of VLANs. Then there's per VLAN spanning tree plus. So it's a Cisco enhancement of STP that provides a separate 802 for each VLAN. Supports port fast, uplink fast, backbone fast, Bpdu guard, Bpdu filter, root guard, and loop guard. All right, and so the 2004 standard, which incorporates 1W, which is rapid spanning tree. And so there is rapid spanning tree, which of course is the 802.1W, and so faster convergence than the original version. Then there's rapid per VLAN spanning tree, so that's Cisco enhancing Rstp with the same changes as they did with STP. And then there's multiple spanning tree protocol, and so that's an IEEE standard inspired by the earlier Cisco proprietary multiple instance STP implementation. So it maps multiple VLANs into the same spanning tree instance. And then there's MST, which is a Cisco implementation of MSTP, which provides for 16 instances of Rstp, combines many VLANs with the same physical and logical topology into the common Rstp instance. Each instance supports port fast, Bpdu guard, Bpdu filter, root guard, and loop guard. So these items that they're talking about here are Cisco proprietary systems you can use to actually sort of fight some common problems for security. Anyway, 802.1 supersedes 802.1W supersedes 802.1D while retaining backward compatibility. So rapid spanning tree terminology remains primarily the same as the original. Most parameters have been left unchanged. Users that are familiar with the original STP standard can easily configure Rstp. The same spanning tree algorithm is used for both versions. Rstp increases the speed of recalculation of the spanning tree when the layer 2 network topology changes, and it can achieve much faster convergence in a properly configured network. Sometimes in as little as a few hundred milliseconds, if a port is configured to be an alternate port, it can immediately change to a forwarding state without waiting for the network to converge. Rapid per VLAN spanning tree is the Cisco implementation of Rstp. And so again, you get an instance on each VLAN. All right, port states. There are only 3 port states in Rstp that correspond to the 3 possible operational port states in the spanning tree. And so 802.1D disabled blocking listening states are merged into a unique 802.1 discarding. And so, of course, learning and forwarding are the same. Root ports and designated ports are the same for both STP and Rstp. However, there are 2 Rstp port roles that correspond to the blocking state. In STP, a blocking port is defined as not having a designated or root port. Rstp has 2 port roles for this instance, so there's backup port and alternate port. So the alternate port has an alternate path to the root bridge. The backup port is a backup to the shared medium such as a hub. A backup port is less common because hubs are now considered legacy devices, and yeah, not many of them about, thankfully. Now, port fast and Bpdu guard. When a device is connected to a switch port, or when a switch powers up, the switch port goes through both listening and learning states each time, waiting for the forward delay timer to expire. So you've got 15 seconds for each, for a total of 30 seconds. This can present a problem for DHCP clients trying to discover a DHCP server because the DHCP process may time out. The result is an IPv4 client without an IPv4 address. When a switch port is configured with port fast, that port transitions from blocking the forwarding state immediately, avoiding that 30-second delay. You can use port fast on access ports to allow devices connected to these ports to access the network immediately. Port fast should only be used on access ports. If you enable port fast on a port connecting to another switch, you risk creating a spanning tree loop. So basically, you're turning off spanning tree on that port. And so you should only do it on an access port for hosts, basically. A port fast enabled switch port should never receive Bpdus because that would indicate the switch is connected to the port, potentially causing a spanning tree loop. Cisco switches support a feature called Bpdu guard. When enabled, it immediately puts the switch port into an error disabled state upon receiving any Bpdu. This protects against potential loops by effectively shutting down the port, and the administrator must manually put that interface back into service. Okay. So over the years, organisations required greater resiliency and availability in the LAN. Ethernet LANs went from few interconnected switches connected to a single router to a sophisticated hierarchical network design, including access, distribution, and core layer switches. Depending on the implementation, Layer 2 may include not only the access layer, but also the distribution or even the core layers. These designs may include hundreds of switches with hundreds or even thousands of VLANs. STP is adapted to the added redundancy and complexity with enhancements such as Rstp and MSTP. An important aspect to network design is fast, predictable convergence when there is a failure or change in a network. Spanning tree does not offer the same efficiencies and predictabilities provided by routing protocols in Layer 3. Layer 3 routing allows for redundant paths and loops in the topology without blocking ports. For this reason, some environments are transitioning to Layer 3 everywhere except where devices connect to the access layer switch. In other words, the connections between the access layer switches and distribution switches will be Layer 3 instead of Layer 2. And so it turns off the need for STP. Okay, so we've hit the end of the topic now. It's a bit of a recap. So redundant paths in a switched Ethernet network may cause both physical and logical Layer 2 loops. A Layer 2 loop can result in MAC address table instability, link saturation, and high CPU utilizations in switches and end devices. This results in the network becoming unusable. STP is a loop prevention network protocol that allows for redundancy while creating a loop-free Layer 2 topology. Without STP, Layer 2 loops can form, causing broadcast, multicast, and unknown unicast frames to loop endlessly, bringing down a network. Using the spanning tree algorithm, spanning tree protocol builds a loop-free topology in 4-step process. They elect a root bridge, they elect root ports, they elect designated ports, and elect alternate blocking or blocked ports. During STA and STP functions, switches use Bpdus, bridging protocol data units, to share information about themselves and their connections. Bpdus are used to elect the root bridge, root ports, designated ports, and alternate ports. When the root bridge has been elected for a given spanning tree instance, the STA determines the best paths to the root bridge from all destinations in the broadcast domain. The path information, known as an internal root path cost, is determined by the sum of all individual port costs along the path from the switch to the root bridge. After the root bridge has been determined, the STA algorithm selects the root port. The root port is the port closest to the root bridge in terms of overall cost, which is called an internal root path cost. After each switch elects a root port, switches then select designated ports. The designated port is a port on the segment with 2 switches that has an internal root path cost to the root bridge. If a port is not a root port or a designated port, it becomes an alternate or backup port. Alternate ports and backup ports are discarding or blocking state to prevent those loops. When a switch has multiple equal cost paths to the root bridge, the switch will determine a port using the following criteria: lowest sender bridge ID, then the lowest sender port priority, and then finally the lowest sender port ID. Stp Convergence requires 3 timers: a hello timer, a forward delay timer, and the max age timer. Port states are blocking, listening, learning, forwarding, and disabled. Per VLAN spanning tree versions of STP, there is a root bridge elected for each spanning tree instance. This makes it possible to have different root bridges for different sets of VLANs. STP is often used to refer to various implementations of spanning trees, such as rapid spanning tree and multiple spanning tree. Rstp is an evolution of STP that provides faster convergence than STP. Rstp port states are learning, forwarding, and discarding. PVST is a Cisco enhancement of STP that provides a separate spanning tree instance for each VLAN configured in the network. It supports port fast, uplink fast, backbone fast, Bpdu guard, Bpdu filter, root guard, and loop guard. Cisco switches running iOS 15 or later run PVST plus by default. Rapid PVST is a Cisco enhancement of Rstp, and so basically combines PVST with Rstp. And of course, it's 1 per VLAN. When a switch port is configured with port fast, that port transitions from blocking to forwarding state immediately, bypassing the STP listening and learning states and avoiding a 30-second delay. You can use port fast on access ports to allow devices connected to these ports, such as DHCP clients, to access the network immediately, rather than waiting for STP to converge on each VLAN. Cisco switches support a feature called Bpdu guard, which immediately puts a switch port in an error disabled state upon receiving any Bpdu to protect against potential loops. Over the years, Ethernet LANs went from a few interconnected switches that were connected to a single router to a sophisticated hierarchical network design. Depending on the implementation, Layer 2 may include not only the access layer, but also the distribution or even the core layers. These designs may include hundreds of switches or even hundreds or even thousands of VLANs. STP is adapted to be added to the added redundancy and complexity with enhancements to as part of Rstp and MSTP. Layer 3 routing allows for redundant paths and loops in the topology without blocking ports. For this reason, some environments are transitioning to Layer 3 everywhere except where devices connect to the access layer switch. There is the logo. So that's us done with Spanning Tree Protocol. So the next chapter is actually talking about Ether channel. And so again, it's to do with redundancy, but it's also to do with speeding it up and also being able to utilize all your links a lot more thoroughly. All right, I'll talk to you then. Have a good one.